All right, we're going to continue with section 15.7 in this video. We're going to work some exercises. We're going to start on page 1055 with number 20, which says in exercises 14 through 20, use Stokes' theorem and equation 9 where appropriate to evaluate the surface integral over sigma of the curl of f dot n ds. So the directions are basically telling us the equation 9 they're referring to in the textbook is the equation that I went over where you can evaluate Stokes or evaluate the surface integral over two different surfaces as long as they have the same boundary curve, and you're going to get the same thing for Stokes' theorem. So they're telling us to use that approach, or of course we could just do the line integral as well, because they tell us to evaluate the double integral. But to use Stokes' theorem to do it means that we would have to do the line integral. So our options, so the directions say to either, change the surface or evaluate the line integral instead of the surface integral. And again, that's because they say in the directions to use Stokes' theorem to evaluate the surface integral, which if we were to evaluate the surface integral directly, we wouldn't be using Stokes' theorem at all. So our two options that they want us to do in using Stokes' theorem is to change the surface or just evaluate the line integral directly. All right, so number 20, they give us vector field f of x, y, z equals z, the quantity z plus 1 times y cubed. So z plus 1 times y cubed, and then negative quantity z plus 1 times xy. So negative z plus 1 times xy. And lastly, e to the x squared times y squared. E to the x squared times y squared. All right. So that's the vector field. But remember, when we're doing a Stokes' theorem problem, we're going to have to take the curl of that, and that's actually what we're going to use in our integration. Well, that's if we're actually going to do the surface integral. If we weren't doing the surface integral, we're doing a line integral, then we would use that as is. So we don't use the curl if we're going to evaluate the line integral. We just use the vector field we're given. All right, so sigma is the part of the surface x squared plus y squared plus z to the 6, equals 1 above the xy plane. N is directed upward. All right, so our surface S is x squared plus y squared, and of course they call it sigma, plus z to the 6 equals 1 above the xy plane. So z is greater than or equal to 0. And I lost the question. And n is directed upward. So our normal vector is directed upward. All right, so now we're told don't use this surface. We have to change the surface because our directions say to either change the surface or use the line integral. So, and we don't know what this surface looks like, but we don't have to be concerned with what that surface looks like. We just have to be concerned with this boundary curve and find another surface that has the same boundary curve. So we're told that z is greater than or equal to 0. So what we'll do is we'll look at this thing when z is equal to 0 and look at its boundary curve in that sense. And then from there, we can choose any other surface that has that same boundary curve. And we can see because x squared, y squared, and z squared, all of those are z to the. So if we were to try to solve for z here, we could, but and the only reason we would do that is Oh, I forgot we can't use this surface. I keep thinking I can go back and use this surface. If we were to try to solve for z here, what I was addressing is if we could use this surface, but we're told do not use this surface, so I can't do that at all. So my hand is forced into finding just a boundary curve for this. So let's look at z equals 0. So when z equals 0, then we end up with x squared plus y squared equals 1. Now, why did I choose z equals 0 of all things to do? Only because we were told that this thing is above the xy plane. So we know that there's going to be an intersection at the xy plane because we're looking at greater than or equal to 0 for our z. So that's why I set z equals 0 versus setting z equal to 5 or z equal to something else. Why did I opt for z equals 0? Because I need the boundary curve. If I set z equal to something else, I'm not going to get my boundary curve. All right, so now let's sketch our boundary curve, and we know what that looks like. And we'll sketch it, we're going to sketch it in 3 dimensions. And then we're going to pick another surface to use. So here's our boundary curve. And whatever surface we use, so you could decide, you know what I want to use. I'm not going to, or actually, let me sketch another picture over here. So that's our boundary curve. We could, I'm just going to sketch the same boundary curve over here. According to Stokes' theorem, I can use any surface I want to as long as it has that boundary curve. So say, for instance, I opted to use whatever this thing is and said, okay, well, I'm going to use that surface. I could do that. It has the same boundary curve and just put a normal vector on there that's directed upward. But then I'm forced to try to parameterize that surface. And I have no earthly idea how I'd even begin to parameterize that surface. So instead, let me use an easier surface. Just use the XY plane inside of that little circle. So that's what the nice part of Stokes' theorem is, that it allows you to use whatever surface. So if you're given something that you don't know what it looks like, something you know what it looks like, but you don't know how to parameterize it, you're given some kind of troublesome surface, as long as you can find the boundary curve of that surface, then you're fine and you can switch to whatever surface that you want to make your life easier. So for instance, I'll draw another surface, same boundary curve. And this one we actually know how to parameterize. So say we had a hemisphere. You could use that surface if you wanted to, and parameterize that. I mean, your life's going to be a lot easier using this one, but I'm just trying to relay the fact that you can use any surface you want to as long as they share the same boundary curve and you orient everything the same way as it was oriented in the problem. So none of these are that surface, but I would just put a normal vector on all of them going up. So I'm going to use this one. And because n was directed upward there, then I'm going to direct the normal vector upward here as well. Now, that upward orientation of the normal vector, if I were to put my little stick figure on this curve, and the surface needs to remain to the stick figure's left as he or she walks around the curve, and the stick figure's head's pointing in the direction of the normal vector, of course, then that would say the stick figure would need to walk in this direction. Which oftentimes when you see a question in the book, that orientation of that boundary curve, what they'll say is that walks in the counterclock or is directed in the counterclockwise direction when viewed from above. So if you were to view this if you could look down the z-axis and look directly down at that surface, then it would have a counterclockwise orientation when viewed from above. So sometimes you'll see that in the wording of some of the problems. All right, so now this plane is the XY plane, and I know that vector right there is just the vector 0, 0, 1. All right, so now what we need the curl of this vector field. And in this problem, actually we'll call this Rn. In this problem, because we were able to easily find a unit normal vector for this surface, we can just go ahead and do that without having to parameterize the surface and then do the cross product. If we were to parameterize this surface, which is just a plane z equals 0, and do the cross product, we would get that exact same normal vector right there. And let's just write down the parameterization so we can see what I mean, because that usually x equals x, y equals y, z equals 0 is what we would use here to parameterize our surface. So we would use our favorite parameterization. So instead of using this surface, we're now using that surface instead, because it's a lot easier for us to work with that surface. And our bounds here would be, excuse me, x squared plus y squared is less than or equal to 1. Or you can use that surface if you wanted to. All right, so now we need to compute the curl of this vector field. So curl of f equals, I'm going to need some space for this, z plus 1 quantity cubed, z plus 1 times y cubed, sorry, and then negative quantity z plus 1 times xy, and then e to the x squared times y squared, sorry. E to the x squared times y squared. So I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. All right, here we are going to get let's see. All right, with respect to partial with this with respect to y, so we're going to get 2x squared y, e to the x squared y squared, 2x squared y, e to the x squared y squared, then minus the partial of this with respect to z, which is just going to give us negative xy, so plus xy. And then the partial of this with respect to x minus the partial of this with respect to z, and take the negative of all of that. So that gives us 2xy squared e to the x squared y squared. Write that down. Now put my negative sign, leave space for the negative sign in front there. So what did I say? 2xy squared e to the x squared y squared, then minus the partial of this with respect to z is just y cubed, so it would be minus y cubed, but then we have our negative sign, so it ends up being that. And lastly, the partial of this with respect to x, all right, and we are going to get negative zy plus 1, or I guess I don't need to distribute, let's just negative quantity z plus 1 times y, leave it like that. So negative quantity z plus 1 times y, and then minus, lost my place, what am I doing? Oh, then minus the partial of this with respect to y, which is going to be 3 times the quantity z plus 1 times y squared. So minus 3y squared times the quantity z plus 1. All right, so there's our curl. Now, this isn't going to, the fact that this curl is extremely messy isn't going to be a big deal for us, because we're going to end up dotting this curl with that normal vector. So we aren't going to have to worry about these first two entries in this curl vector. But just so we remember, that's M, this is N, and this is P for the problem instead of the vector field that we were originally given. So now we're going to do the surface integral. The surface integral over S1, because we opted not to use S, or we were told we couldn't use S, and we chose a new surface S1 of curl of F dot N ds equals the double integral over the region R, and that's the region R right there, of curl of f. I don't want to write this whole thing out again, so I'm just going to write curl of f. And then we're going to take that and we're going to dot that with our normal vector, which is 0, 0, 1. Keep in mind, in practice, you normally would do r sub x cross r sub y for your parameterization for your surface to get this right here. Then dA. So remember, this ds, this is just a notational thing. So that's a surface integral, and it says we integrate with respect to surface area. But when we switch to a double integral, then we need to switch to our region R, and we integrate with respect to area for double integrals. All right, so now see what do we end up with here. So now keep in mind here, you don't take your curl of f as is. You have to take your curl of f and you have to substitute in your parameterization. So all of the x's we're going to change, quote unquote, change to x. All of the y's we're going to change to y's, and all of the z's we're going to change to 0. So we don't even have any z's up here, do we? I mean, those are going to disappear anyway. But here, I didn't write it out, but really at that point right there, we should be just substituting in z equals 0. I didn't want to write this whole thing out again just to put in zeros for z right there. Instead, we'll just do it on the next line. So this ends up being, when we put z equals 0 in right here, we end up just with negative y. And then z equals 0 over here just gives us negative 3y squared. So we end up with negative y minus, well, this, comma, negative y minus 3y squared. But I'm going to go ahead and do the dot product. So just pretend we have this, and then negative y minus 3y squared. That's what really goes right there. We dot that with 0, 0, 1. Those two terms disappear, and we just end up with this term right here with zeros plugged in for the z. So we get that this equals, oh, you know what I did not specify is, should we be doing the plus or minus? We should have the plus here, but I forgot to specify that. So let me go back up and do that in just a second. So the double integral over r of this dotted with 0, I mean this times 0 plus this times 0 plus this times 1, but this with zeros plugged in for the z, gives us negative y minus 3y squared dA. Now, should we have a plus sign or a minus sign in front of here? Let's go back up and check. So we were told in the problem that the normal vector was directed upward, and the normal vector, we directed our normal vector upward on our surface that we chose. So that means we're just going to keep the plus sign. So we don't need to put a negative sign out front here. So now, because that region R is a polar region, let's set this up using polar. Take this integral and change it to a polar integral. So 0 to 2 pi, and then 0 to 1 is our radius, and then negative r sine theta minus 3r squared sine squared theta. And then we need our Jacobian r, and then dr d theta, and you would evaluate that integral. All right, so I'll stop this video here, and then we'll continue with section 15.7 in our next video.